Welcome back to section 2 of chapter 7. In this section, we are going to be looking at finding the area between curves. In the last section, and for the last couple chapters, we've been finding just the area under a curve. That we may have called it different things, but that's what we've been finding. When we find the antiderivative or the definite integral, we find the area under the curve. So, if we're looking at the curves on this slide, and we wanted to find the area under the black curve from, let's say, our intersection points from here to here, the area under the black curve is going to be that area minus this little bit over there that I overstepped. If we wanted to find the area under the blue curve, it would be that area. Now, if we wanted to find the area in between the curves, it would just be that area under the black curve minus the area under the blue curve. That gives us what's left of that black area. And that's the basic premise of what's going on in this section. So looking at a problem, here we have a blue top equation and a red bottom equation. It is important to get that distinction between the top one and the bottom one. When you first start out with problems, most times it's just going to give you the equation. I recommend graphing. And then once you have a graph, you can see the top and the bottom. What we have is we're going to find the direct integral of the top, because that's going to find this area underneath. And then we're going to find the direct integral of the bottom one, which finds the area underneath that one. And then if we subtract those two, we're going to get that area in the middle, which is what we were looking for all along. And so this actually is not any different from what you were doing in geometry. If you have a washer and you're trying to find this area, or a target and you're trying to find this area, you take the area of the big circle minus the area of the little circle. Same thing if you had squares. The area of the big square minus the area of the smaller square. It's exactly what we're doing here. And so to find the area, it's just the area of the top minus the area of the bottom. From A to B, in this case, A to B is going to be from 0 to 1. And so we can plug it in. It's the area of the top one minus the area of the bottom one. Now, in being the integrals, you can break them up with subtraction. You can also combine that subtraction. So this integral is the same as that one where we just combine it into one. Which one would you use? Well, if you're going to be finding it by hand, you're going to end up breaking it up anyway. So you could break it up. If you're finding it using a calculator, you would probably want to use the one where they're combined, the second one. Then the second one's going to be useful for a lot of the rest of the chapter, but being that we're going to be adding, subtracting, you can have them broken up. So we can either find this by hand or we can find it using the calculator. I'm actually leaving that to you for one of your exercise or warm-up problems actually. But when you do that, you get the shaded region as 1/3. So I say you can do this using your calculator. On the AP test and most tests, this topic is going to be on a calculator OK section in almost every instance. And as such, it's important to know what to do. It's important to know how to do it. This one's pretty easy to find by hand. There are some where finding it by hand is not particularly an option, or if it is, it's going to be a very time-consuming one on a test where time is going to be an issue. So knowing how to do it on your calculator is good. I know personally, and as a teacher, for a problem like this, I recommend doing it by hand so you can practice your integration. And we just had one chapter on it. That's not a ton. All that practice is going to make you better, but then check it using your calculator. If this was a test and you were using your calculator, you always need to set it up. If I was doing this problem on the test, we would have the area and it equals, we have the integral. We know the bounds, it's from 0 to 1. That's basically given to us. And then the integrand, or the argument, the x, we have the area equals that. Area equals 1/3. That's all the work that you would need on this problem. On the AP test, this chapter generally lends itself to one free response problem. This would be part A. Part B would be section 2. And part C would be section 3 or 4 of this chapter. So this right here is usually 2 points or so out of the 9 on that problem for the AP test. You get 1 point for setting it up, possibly with the bounds, possibly not, and 1 point for the answer. Sometimes, depending on the difficulty level of this problem, it's only 1 point for the answer and or for setting it up with the correct answer. But we'll get to more about that at a later date. So the premise of this topic is, again, pretty straightforward. It's just the integral at the top minus the integral at the bottom. A couple things that they could do to make this more difficult. First, obviously not giving you the graph to begin with. Graph it. A lot of times you'll have a calculator, but sketch the graph, even if you don't have a calculator. You know what a square root looks like, you know what the squared looks like. But then next, a lot of times you have to find what those bounds are. You have to find the 0 and the 1, those intersection points. How do you do that? You set them equal to each other. We know that we have the square root of x and we have x squared. Well, where is root x equal to x squared? Couple ways we could do this. We could square both sides to get x equals x to the fourth. Subtract, you can factor out an x, you end up getting 0 and 1. That's one way. In this one, graphing it looking like, oh wait, it looks like 0 and 1, plug them in. Oh, turns out it is 0 and 1. Those are equal. Using the intersect feature on your calculator, a lot of times these bounds won't necessarily be nice numbers. You might have about 0.5723 and about 0.1439. You find those once in the question, that'll take you through the rest of the question using those same bounds. You can actually save them to variables in your calculator too. But so you could use the intersect feature of your calculator for that. Either way, finding those bounds is one of the things that can make these problems a little bit more difficult. That's just algebra work. That's not calculus work. It's just algebra work, or even calculator work. So that's one. Another thing that can make this type of problem more difficult is having something like this, where as we're looking at this, which one's the top, which one's the bottom? Well, obviously red's the top and blue's the bottom, but over here, red's both the top and the bottom. This problem is easier to, or it is possible to do like this. We would have to split it up at this point, and here we'd have the positive red minus the negative red, then plus the integral of the red, positive red minus the blue. That's not necessarily the easiest way of doing this one, though. And there's also times where that doesn't work at all. For instance, if we had two equations that looked like this and this, and we needed to find this area in between them. We would not want to try to do that vertically like we did before. So instead, we would use we'd have to switch the axes. Instead of the top and the bottom being the top and the bottom, we'd want the top and the bottom to go this way, where blue is actually now the top. It's the furthest away from the axis. And the red is the bottom because it's closest to the axis. When you do this, you have to switch all of your x's and y's. We don't want y equals plus or minus x. Square it. This is the same as x equals y squared. And here we can add 2. X equals y plus 2. Now we have them in terms of y. So we can set up our integral. The blue one is further away, so we're going to have y plus 2 minus y squared. This is going to be a dy because we're finding rectangles just like we were. The height of the rectangle, the width of the rectangle is now this dy, that little tiny increment there. And we need to know where we're going from. We're going from here to here. The y values, everything has to be a y value. We can't use the x values. We would find them the same, just set them equal to each other. Y squared equals y plus 2. Subtract over. Y squared minus y minus 2 equals 0, factor. We have y minus 2, y plus 1, which means that y could equal 2 or negative 1. There we go. And then we can solve it. This one, again, you could do by hand. This is the second warm-up problem to check the work on this one, or you can plug it into the calculator. If you do, plug it in using x's. It would look exactly like this. You'd still go from negative 1 to 2, and then you'd have parentheses x plus 2 minus x squared dx, because x is your variable. Trying to plug y's in there might make things weird, but x is the variable. It's fine. You're still going to get the same answer. And when you do, the answer there, by the way, should be 4.5. So you're going to check the work on that and see if it's 4.5, see if you can plug it in correctly. And that's the second warm-up problem. Notice here that we went below the axis here. That's okay. That's not even because we're going sideways. We could have graphs where we have the axis. We could have the big one, and we could have the smaller one. Changes nothing. It's still going to be the integral from whatever a and b are of the top one minus the bottom one, dx. So it does not, like where the axes are, does not make a difference, because this negative down here, when we subtract it, it's going to become positive. It's going to add to that area. It's beautiful how it works out like that. Anyway, so this, again, this section is a direct, it's a direct extension from what we were doing last chapter, where we just have two things now, and we subtract them. Again, the calculus part of it is not any more difficult. Setting it up, making sure you have the setup right, making sure you have the bounds found. That stuff is the stuff that's going to be a little bit tougher than what we were doing last chapter, but it's still a great place to start a chapter. So be working on the problems, but keep working on problems, keep asking questions, and as always, happy mathing.